All right, so welcome everyone to the second day of the workshop. Today we start with Kris telling us about cohomologically tropical varieties.
Thanks, Felipe. Thanks to the organizers, Oliver, Felipe, Lynn, and Kris. Thanks for coming. This is a talk based on work with three co-authors. Edward Axlis is my former PhD student in Oslo, Omid Amini in Paris, and also his former PhD student, Mathieu Poincaré, who's now in Nantes. And what we study in this work is when can we recover the cohomology of an algebraic variety from its tropicalization. So I'm going to go through first what tropicalization is and the kind of more fundamental question of what in general does a tropicalization know, in quotes, about the original variety. So knowing is also comes from decoding. There's some combinatorial invariants that maybe tell us something about the original algebraic variety. So we're going to just stay really basic and have one single variety X in the complex torus. And the tropicalization, I'm going to take it as defined if you know constant coefficient tropicalization or trivial valuation tropicalization. I'm going to give this kind of more complex analytic description where we just take the limit as t goes to infinity of log base t of the coordinate-wise log of x. Okay, so in this simple example of a line, so here's a picture of the real points of a line in a two-dimensional torus. And in order to take the logarithm, of course, we have to take first absolute values of the coordinates to be able to apply log. So to break down this map, the first step of taking absolute values, we get this rectangular region, and the complex value solutions to this equation equals 0 land on the inside. And then taking log stretches this out into a shape that looks like an amoeba, and this is actually called an amoeba of Galfin, Kaprasov, and Zelevinsky. And taking the base of a log to go to infinity makes this amoeba retract onto the skeleton. That's this tropical line that many people have probably seen. Okay. So this is kind of the logarithmic limit set, or the cone over a logarithmic limit set in the sense of Bergman, a very basic way of tropicalizing. So some things that maybe people in this room know, or maybe some don't. Some partial answers to this question. Well, the tropicalization always knows a dimension. So this was real dimension 1. This was complex dimension 1. So it contains dimension. There's a sense of which it retains the degree. There's a sense in which this is a degree 1 tropical variety. And this, well, it's in the torus, but it's compactification to the projective plane. It's degree 1. There are also invariants in enumerative geometry that we can recover under certain conditions. So all of these stars mean they're caveats. There are certain situations where we can say things about intersection theory, enumerative geometry, rationality questions in terms of field of definition of our varieties, term classes of the varieties. Even, well, there are known instances where we can recover the cohomology, things like Hodge numbers. But all of these have caveats. They don't work for just any variety that you tropicalize. And since we're in a workshop about matroids, I should say that often these caveats come down to the variety that we tropicalize being a linear variety like we have here, and then the tropicalization being the matroid fan, the matroid associated to that linear space. Okay, so let's look at an example, or a few examples of varieties and their cohomology. So,
Presents a question.
Yeah. To start with a toric variety, do you get the fan?
We'll get to tropicalizing toric varieties in a bit, and we get something that's kind of dual to the fan. So there's a notion of extended tropicalization due to Champagne, and we're going to use that in the talk, but so far we're going to start with just the open torus, and its tropicalization is just Rn. Okay, yeah, please interrupt me with questions. Okay, so here's the actual complex points drawn, right? So we had a line before, and I drew the real picture. It was a real line with 3 punctures, but the complex line with 3 punctures, this is like CP1 with 3 holes, so it's a sphere with 3 holes. And here it's, well, okay, I wrote homology groups here. These are maybe well, they're linearly dual to the cohomology, so it's not so bad. And there's a tropicalization. Here's another example where we have two different varieties. So we can define a different curve in C star squared that has this topology. So like a degree curve, two curve that touches the axes in 4 points. And it tropicalizes to this cross figure. And we can also have a singular curve in C star squared, which is a nodal curve that also has 4 punctures, 2 on each of the spheres. And its tropicalization actually ends up being the same thing. Okay. However, the cohomology of the homology and cohomology of these two spaces is different. Okay, so this is already saying that there is going to be no way in this example to recover from this picture, which is the same, without any extra data, the cohomology. Okay. However, in the top one, we'll see that we can. So what we want to be able to do, first of all, is we'll at least have some recipe, some candidate for vector spaces from the tropicalization that could, in some cases, coincide with the vector spaces we have here, which is the homology. So this is a recipe due to Itenberg, Katzarkov, Mikhalkin, and Zharkov, who introduced something called tropical cohomology. And they're so-called multi-tangent spaces. So now we'll stick to a case where we have there's one thing that very important thing that is written on the slide that I forgot to say, for those not familiar. This tropicalization, it's a subset of Rn, okay? But it has the structure that there exists a polyhedral fan sigma, okay, whose support is that set. So we have a set, but we can equip it with a fan structure. And choosing a fan structure is something we're going to do all along in my talk. And eventually it will be irrelevant which fan structure you choose, but we will work with fans. Okay. So now let's say we have a polyhedral fan. And it'll be rational in the sense that the cones are generated by integer vectors. Okay. I'll often assume that it will be simplicial, but for now this is good enough. And here's how we define for each cone of the fan some vector spaces. So these are vector subspaces of the pth exterior power of q to the n. It'll take rational vector spaces. And what we do for a face is we look at all the cones that dominate that cone, including itself if we have to. And we just take the vector subspace generated by all of the p wedges of the spans of those bigger cones. Okay. So here in our ongoing example, if we look at the vertex of the span, 0 underline, then and we take F1, then all the directions we can go in from this vertex in any ray that spans the entire 2-dimensional vector space. Whereas if we take just this edge, right, then there's only this edge itself that dominates it, so we can only go in the vertical direction. And then things get a little more complicated. Here in this 2-dimensional example, we can look at what happens, say, on this edge or this vertex, and here are the dimensions. Or the even isomorphisms. Okay, and I'll let F upper P just be the linear dual. Sorry. So the other thing that we can notice here is that this is not just a collection of vector spaces, but this here actually defines a functor. So whenever I have two different cones related by an inclusion, I actually also get a map between the vector spaces. So there's a natural inclusion from this F1 of this bigger face to this F1 of this smaller face. Yeah.
All right, could you explain the second diagram? I just wasn't listening when you said it.
This one, okay, I went kind of fast, but let's see. So let's take the origin here. And let's take F1. Okay. So the rays here, they have their directions written on them. And from this point, I can, even just using the rays, I can go out in all directions of the 3-dimensional space. Right. So, and that's the most we can do because we're in 3 dimensions. Now, if we want to take F2, okay, we need to look at all the faces still that dominate this. Well, if I take a 1-dimensional face, its span is 1-dimensional, wedge 2 of that is 0. So that's not going to cut it. We have to go to at least 2-dimensional faces. But we see that, you know, we can get any possible second power in Q2. Like at E1, wedge E2, E2, wedge E3, E1, wedge. Okay. And if I go to an edge, we see that, well, this one is still the same. I can still go in any direction for F1. But the 2 powers, there's this balancing condition here in tropical geometry, or you can just use the fact that I've written the vector directions to check that even though I have 3 faces of dimension 2 near this edge, there's a relation among the generators. So I only get 2 dimensions this time. Okay. But what's important here is that a recipe for vector spaces for each cone. And not only that, but we get system of maps too. So one way of saying that is these are functors from the category of which is given by the fan. So we have objects being faces, morphisms being inclusions, and one of them is a covariant functor and another is a contravariant. Any other questions? Does it come from? The question is why? And the answer to that is this motivating example, and one of the reasons we're all here, which is coming from matrix. So if we are in the situation like in the first example, where we take a linear subspace of the torus. So what I mean by that is there's a compactification of the torus to CPN such that the closure of our L is actually degree 1. Okay. And then, well, the complement of this compactification of L and its compactification is going to be a union of hyperplanes, hyperplane arrangement. And the hyperplane arrangement has then a matroid. So I'll call that the matroid of L. So it's the ground set is a set of hyperplanes, and the rank function is just the codimension. Oh, sorry. Yeah, in PD. So this is a D-dimensional space. The codimension of PD of the intersection of the hyperplanes indexed by that set. So here's the motivating example with the kind of combination of 3 theorems that in the end says that in this case, the tropicalisation of such an L knows the cohomology of L. Okay, so kind of is a combination of these 3 theorems, which says that first one due to Driscourn and Orlock-Solomon, which actually goes back to a conjecture of Arnold that says that this cohomology group of your L is in fact determined combinatorially, determined from the combinatorics of the matrix. Okay, so we know that there are many different linear subspaces that have the exact same matroid, right? We saw realization spaces yesterday. But you take any 2 in that same realization space that are defined over C, and they'll have the same cohomology. Okay. This does not mean that the topology of L is determined by the matroid. So it's known that there are examples where the fundamental group of L and an L prime that have the same matroid, but they're not equal. Yeah.
Do you include the ring structure in this?
Yes, thank you. Yeah, so this actually, the ring structure is also determined by L, or by the matroid, sorry, of L. And it's actually a recipe of this, just from the so-called circuits of the matroid, given by Orlock-Solomon, that's called the Orlock-Solomon algebra. And that recipe generalizes to any matroid. So for any matroid, there's a Orlock-Solomon algebra that in this case specializes to the cohomology.
Is this the Orlock-Solomon algebra or the reduced Orlock-Solomon algebra?
Thanks, reduced. Great. Okay, the second theorem of Zharkov says that the tropicalisation also only depends on the matroid, right? So if you have 2 different linear subspaces that have the same matroid, you won't see a difference in their tropicalisation. But of course, there could still be something that goes wrong with tropicalisation, and you don't get to recover this cohomology, even though both are kind of combinatorial. And the last theorem that, well, okay, so I proved without the ring structure a long time ago, and shortly after Zharkov proved with the ring structure, is that this Orlock-Solomon recipe from combinatorics for the cohomology, you can actually recover it from the fan. So let me just be a little bit more precise here, because in the last slide, right, this had a subscript sigma for a fan. And the sigma should have the property that the support of sigma is equal to the tropicalism of L. Okay, so take any fan structure on the tropicalization of L, use the recipe from the previous slide to get the vector spaces from the at the origin of the fan. And there's a ring structure, which I will just sweep under the rug, but it does exist there, and it comes from the exterior algebra. Okay,
The fan could be non-simplicial.
so it doesn't really, so this recipe, I mean, I gave a recipe in terms of a fan structure, but there are all kinds of ways of just coming just really from this. Okay, to define what we're going to do next, we do want the fan structure, and because we'll want to bring toric varieties into the picture. Any other questions? Yeah.
Can you classify the matroids that give you smooth bands?
What do you mean by smooth? You mean like?
They correspond to a smooth toric variety, regular band.
So they're all, okay, so if you want to, yeah, okay. In a sense, let me be careful here. So when we tropicalize L, this has no fan structure. This is a set. So the sigma that we put on it is a choice. You choose a unimodular fan, you're good, right? So there are, thanks to Federico Ardilla and Carly Clivens, there's one very nice kind of maximal fan structure like related to maximal wonderful compactification that comes from the combinatorics. I mean, of course, there's all kinds of fan structures we could put on here. That's a unimodular fan structure. There are also other building sets related to other wonderful compactifications. They're all unimodular. Any other questions? I'm going kind of fast. This is a problem with slides, so feel free to interrupt.
Oh, okay.
Yeah.
Is it true integrally?
Yes. Yes. But our main theorems, we're gonna need rational coefficients because we're gonna use the Billian weight vectors.
Yeah.
So our kind of main question started with this project was, for what other varieties does such a thing hold? For what other varieties can we recover the cohomology, say put X here, from these vector spaces? Okay. And that question we actually couldn't answer. We had to make stronger demands where we don't just want to recover the cohomology of some open, right? This isn't a torus, so it's not compact algebraic variety. But where we want to look at compactifications of this and demand that our tropicalization knows the cohomology of all the strata. So I'm going to explain what I mean by that. And then this is really where our choice of fan structure comes in, at least temporarily. So what we're going to do is we're going to look at so-called tropical compactifications in the sense of Debelev. And again, our notation, we have an algebraic variety X, mathcal X, and the tropicalization will be usual X. And we'll fix a rational unimodular fan. So now we know that this sigma that has support X is going to give us a non-singular toric variety. It's not complete, right, usually, but it's at least a non-singular toric variety. And the theory of tropical compactifications of Debelev tells us that, well, with this condition, the closure of our X in this toric variety is going to be now compact. And moreover, it of course has this nice stratification where each of these open strata is in correspondence with, okay, sigma gives me a cone of this fan, which gives me a stratum of this toric variety, and I'll let X upper sigma be the intersection of this with that stratum. Okay, so this is a nice open stratified space. And well, there's various different ways of looking at it. We can, in order to tropicalize this, we can use the extended tropicalization due to sound, thanks to sound. And we get some kind of topological space, which I don't even think I'll draw any pictures of, but it exists, and it's somehow in a dual cell structure to the fan sigma. But if you like, each one of these strata lives in some lower dimensional torus. The lower dimensional torus coming from this toric stratum here. And just tropicalize that, like we did before. Subvariety of a torus, and tropicalize it, and we get some X sigma that also has some fans. admit some fan structure. Okay, so here's our very basic example of the line again. Right, here is the fan. The toric variety of this fan would be P2 minus the 3 toric invariant points. But if I compactify this line there, I still close up these 3 holes. The one at infinity and these 2. X bar is really P1. Okay, and the tropical compactification of the tropicalisation is really still just throw in 3 points at infinity. Okay. So now we actually want to do some tropical cohomology. And to do that, what we'll do is we'll extend this functor FP. So now we pick up all kinds of extra faces in this closure. They're still all cells. This is a cell complex. Once we've put a fan structure on our X. Okay, so just think this is some cellular complex. And now we want to extend this functor to also have a recipe for what it does to a face that we've added on the boundary. I'm not going to give you that recipe directly. It's not too hard to explain, but it's kind of not really worth it for our purposes. What's important is that this is still a functor. That there's still maps between the different vector spaces of faces that are related by inclusion. Okay. So here's how we get the tropical cohomology. I'm going to say the kth tropical cohomology group of this X bar is going to be the direct sum over some bi-graded vector spaces or indexed by vector spaces indexed by PQ. And HPQ of X bar is going to be the qth cohomology group of some cellular chain complex associated with FP. Okay, so what is this? Here's the PQ chain group, PQ, where I take the sum over the q-dimensional faces of X bar and just take the FP of that face. Okay, so that's a chain group. We then would of course need also the and how this differential works. Well, a cellular differential, we know how cellular differentials work. We'll have to have orientations on the cells and all of that. But here we don't just have one-dimensional vector space for the cell like this. FP vector space. But we know that we have these kind of, so they were dual to inclusion maps, right? But we have a map here. Just if tau is a face dominating sigma, we have a map between these. So we have this map for the individual vector spaces and we compose it with an orientation map of the usual differential. Now we take tau of dimension p. Okay, so these are, this is an instance of cellular sheaf cohomology. Okay, it's also much more flexible. I could put lots of different things here. I could put in kind of an open subset of X bar in the so-called Alexandrov topology or even in the Euclidean topology. I could also put X here. I could put compactly supported cohomology here and define variants of that. So there's all kinds of different variants of this. Some will appear later, but just keep this recipe in mind and know that there are ways of tweaking it to get different, slightly different. And this is computable in polymate, so this is all implemented. People do like to do computations. The tropical compactification of tropical varieties and this cellular sheaf stuff. Any questions?
Can you repeat again how you get this tropical compactification? I know it's on the last slide.
Yeah, so there are ways of describing it combinatorially, but here's one way of getting it is just do Sam Payne's extended tropicalization. Okay, but let me say a little bit more about what the structure of this space actually looks like, because I said this also has a cellular structure. So what do the faces look like? Well, this example is not very enlightening. It just says put a point at the end of each ray. But let's say we have something that's kind of two-dimensional. I have this two-dimensional fan in a previous thing. So each pair of rays here spans a two-dimensional cone, and that would be unbounded. What happens when we do the tropical compactification of such a thing, or actually anything when the fan sigma is simplicial, so or even unimodular, so that's stronger, is that each one of the faces becomes a cube. So it's kind of like a cubical compactification. Of this. So in some sense, this should be kind of a bit straighter. Okay, but topologically, at least, and topologically in the sense that the stratification that we get from X bar, each one of the faces is a cube of its dimension. A square or a segment, or if we have something 3 dimensions, we get 3 dimensions. Okay. And there are very convenient ways of indexing where these new faces come from. They come from pairs of faces. Other questions?
Could you say again what coefficients you're using in the cohomology?
For the cohomology, so everything is rational coefficients. Some things still work with Z, but our main theorem is with rational coefficients.
Can you say anything integrally?
So in this example, this is this motivating example. This is also integral. So there are integral variants of this. Basically because we have a rational fan, so each cone is parallel to a lattice. So we can also just take the Z points in each cone and this sort. But, and where did it go? You can define all this also with Z coefficients and ask what you get. But our main theorem is with, it's the cone, we'll be with D coefficient.
Okay, sigma is in X bar or is little sigma in sigma? I'm trying to parse the.
Say again, this one?
Yeah, sigma is a point in X bar.
Yeah, so I'm kind of abusing the fact that this X bar is a set, but it also carries a cellular structure. Okay, so to be precise, I should probably, say, okay, X bar is a set and maybe call X cell this cellular structure on it. So this is a collection of cells. And then, does that make you more happy?
Yeah.
More precise? Yeah, thank you. Okay, so. Other questions? Okay, so here's our basic example of aligning it. Okay, so where now we're gonna try to look at these chain groups and the differentials, so the tropical homology eventually of this example. Okay, so P, I forgot to say, P equals 0. This is the case of just constant Q coefficients. Okay, so cellular cohomology of this thing, if I just using Q coefficients, I have 4 vertices. So I put a Q4 here, and I have 3 edges. I put a Q3 here. Okay. And well, we know that this is surjective, so we get H00 is just. Now for P equals 1, we have to go back and remember at least what we said. At this point, we get a contribution of Q squared, Q2, 2-dimensional vector space. And I didn't tell you how to extend it, but let me tell you now, these all get Q1 is equal to 0. So I just get Q2 here. And then for each edge, I have a 1-dimensional vector space for the F1. That's the one parallel to it. Yeah.
So your form, on the infinite points you're adding, your forms have to be kind of 0 in the direction of the infinite point of that works.
You're already talking form. There is a even differential form variant of this. There's also just a completely, the right definition combinatorially coincides with that intuition. Exactly. If you, another way of defining this FP is think that this point is living in some tropicalization of a different toric stratum, and you're going to use the same recipe for FP, but only looking in that stratum. You don't look at faces that are bigger that are outside of that stratum. And then you see that that's going to F1 should be 0 because there's no 1-dimensional faces in the same stratum. All right, so you can then compute that this is injective. This map. So we get a H11 Q is H11 of X bar is equal to Q. Okay. And these other two are equal to 0. So what we get when we remember that, H2 was the direct sum over all PQ summing to 2, we get Q, 0, and which happily coincides with the cohomology of the scale. Right? Well, we have this arrow here, trop, but this arrow trop is not a possible map. It's not a topological map. You can't pull things back along this in, with the description of tropicalization that I gave. We're going to use other more analytic spaces to tropicalize where we can actually pull things back, the Berkovich analytic spaces, but we're just using, we really want the complex algebraic variety here. So we need to figure out some way of not just saying, we have vector spaces that are the same dimensions. And so we're kind of happy, right? There's so far nothing functorial here, it's just a coincidence, if you like. Yes.
Comparison theorems with a complex variety and backward space, and then just go back to the backward space.
We still don't know though when the tropical cohomology is reflecting the cohomology of the vector space, not even like for curves. So that's even more complicated. Yeah, that could be another way around it. Because what I'm going to do now is define a map from the tropical cohomology to the cohomology, and you're going to see that it's kind of cheating. So I would love to have different candidates for this map. But this is what gives us our definition of what it means to be,
So just to make sure, this cohomology you are defining does not remember the weights of the fan. Weighted, you are.
Good, yeah, excellent. So for now, the recipe that I've defined for just the cohomology does not remember if we have in a tropicalization, we usually associate weights to faces of top dimensional cones. This doesn't see that. There are operations we can do on cohomology. So we're going to see it in a bit. There's a cup product and a cap product between cup product on cohomology and a cap product between homology and cohomology, and a way of defining fundamental classes, and the weight should come in when you define it. Okay, so here's a definition of cohomologically tropical, and well, what it comes to us from after defining this map, tau star. So we had some disagreements with co-authors of whether to call this tau star because this is still not like a pullback map. I'm going to tell you what side I was on. This is not an honest pullback. Okay, and we'll see also that it is kind of cheating, or at least something to be desired. So if you have other candidates for how to do this, I would love to hear it. So remember that this here is a direct sum of HPQ of X bar. So the first thing we're going to do, which is already possibly losing a lot of information, is project to the diagonal. Just project to the HKK parts. Okay. So yeah, so I should just say that this map that's horizontal is going to be defined by going this way. Okay, so this thing commutes. The next map actually comes from, so this is work of Amani and Kris. Which relates the tropical homology, or the diagonal part of the tropical homology, to the Chow ring of the toric variety that we're compactifying. Okay. So, well, this thing we've seen the definition of. This thing I think many people know a definition of. You can take this as this is a quotient of a polynomial ring, and the generators are indexed by the rays of the fan. Okay.
No one on sigma.
No. Oh, well, okay. Unimodular.
That's it.
That's it. Yeah. So, in a sense, if you love like Chow rings of matroids, or you love the Chow rings of toric varieties, okay, this is one reason maybe to think, oh, okay, now I have a cohomological definition of that, right? And also even extra information, because I have the PQs for P not equal to Qs. So there's some extra information about that. I should maybe also say that people might have seen the Hodge spaces for fans of Michel Brion. This is these are different. If you know that and you want to know the difference between them, I'm happy to say so after my talk. They kind of market this theorem as one instance of the Hodge conjecture for tropical varieties. I should put an instance. So there is a variant of a tropical Hodge conjecture that basically asks if stuff here satisfying a condition, which in the case that this is the support of a closure of a rational polyhedral fan, okay, everything satisfies that condition. This is stuff here satisfying some conditions can be represented by so-called algebraic tropical cycles. And the algebraic tropical cycles are coming from here in this case.
The lateral map goes the other way.
Yeah, but it's an isomorphism. You're absolutely right. You're absolutely right. You're absolutely right. And here we see that map going the other way. So June's comment is that the natural map is if you think of this as being something algebraic or from the ambient toric variety, right? And you have a subvariety, well, you get a map from here to here. Okay, let's put map cal x here, right? Because I still don't think there's much of a natural map here if you're not an expert in tropical geometry. But in algebraic geometry, the natural map is this cycle map that would take algebraic cycles from the ambient space, intersect them with your subvariety, and then take the cycle map. Okay. All right, so project isomorphism, maybe in the opposite direction than what you would think is natural. And then from here to here, so remember now, this is a non-singular toric variety. It's not necessarily compact, but in a sense, these are the kind of compactly supported algebraic cycles, this description, and we can map this via the cycle class map to the usual cohomology. Okay. And then the last map, here we have an honest inclusion of X bar into CP sigma. So we can now pull back via that honest I. This is honestly a pullback. Okay. So already we see, okay, so that's the map. Now the definition to be cohomologically tropical with respect to the sigma, right? So remember that sigma is hiding out here in what this X bar is. This X bar depends on the sigma that we've chosen. And of course, this also depends on the sigma that we've chosen.
It's also the upper rightmost one, right? The compactification of X.
Yes, sigma is everywhere, even where you don't see it. Everywhere you see a bar, there's a sigma hanging out. Right? Yeah, so this definition is, or even this map, how it works is, yeah, the spaces are dependent on sigma. And we say that it's cohomologically tropical if for every cone of sigma, this map tau star that we've defined above is an isomorphism. Okay. Yeah.
Check. Those are the closed variety.
Yes.
The closed.
This map is defined on the closed variety. Next. Yeah. Yeah.
I'm sorry, I'm not an expert, but in the integral cohomology of the complements of certain arrangements.
Yes.
They have a natural bigrading that arises directly from the combinatorics. Is your bigrading related to that?
When the theorem holds, and the theorem is to come, in a sense. So bear with me. But I mean, I'm assuming that the bigrading you're talking about, I mean, it's coming from the mixed Hodge structure.
Well, it's coming from an underlying superficial complement.
But does it coincide with the one from mixed Hodge structure? The filtration that you're getting.
That's what I don't know.
Okay, let's maybe talk after talk. That's what I would imagine, and that's kind of in a sense part of what we covered. Okay. All right, so this is much stronger. Well, first of all, I started motivating the question with the example of linear spaces, which were open things, okay, and saying something works. Now I've made things much more complicated. Well, I've taken compactifications, and I'm also asking that not only is it, working for this, is this an isomorphism for this compactification? I'm asking that it's an isomorphism for every stratum. Okay, so kind of strayed a bit, but this we can actually answer. So here's the theorem, and let me take a sip of water. Because, well, in a sense, for me anyway, it leaves something to be desired, but it is an if and only if. So Already the map tau leaves something to be desired, so we've forgotten some things. And it feels a little bit cheating, but it is an if and only if statement. Granted, we start with the assumption that our X was Schoen subvariety of the torus. So if you know what Schoen means, that's great. Another way of equivalently saying that something is Schoen is that each of these, so this is the open stratum corresponding to sigma, that this is non-singular for every sigma. Okay? So if we have that assumption, then we can say that X is cohomologically tropical, CT, if and only if we have two conditions. One condition is really kind of purely combinatorial and tropicalization. It's that this tropicalization X is a so-called tropical homology manifold. It's underlined because I'm going to say what that means in a second. And the second condition is that the algebraic variety X is not only Schoen, but it's something that we call wunderschön. And nicer than Schoen. And you'll see how it has to be extremely nice. We'll get to it in a second. But one thing I want to point out, so yeah, okay, so the sigma is kicking around here, but that's just in my way of describing to you what Schoen means, but there's really no appearance of sigma in this theorem. Okay, and part of what we also prove is that this condition of being cohomologically tropical, and well, also this condition 1 and 2 here, these two conditions, are completely irrelevant of the fan that we choose. As long as we choose a unimodular fan whose support is the tropicalization, if we choose any other fan, sigma prime, it works for one if and only if it works for the other. Okay, so.
Is that a corollary of the theorem or is that used in the proof of the theorem?
It's separate. It's separate. So I mean, to kind of formulate this, right? I mean, you do have to fix a fan structure in order to even talk about, the maps tau star that you want to be isomorphisms. Okay. Yeah.
This tropicalization doesn't depend on the fan.
The tropicalization is just a set. This open tropicalization is just a set. Okay. Once we fix a fan structure, then we can define X bar, we can both X bars, and so on, and the maps tau. Right, like I mean, Schoen is something, think of it this way, if you know what Schoen means, you know that's something intrinsic about the subvariety of the torus. But another way of formulating what Schoen is pick a fan structure, pick a fan, compactify it, and say that all the strata are smooth. But then you pick a different one and you should still get that they're all smooth. So, yeah.
But wunderschön also depends only on the open strata.
Yeah, and you'll see why once I get the definition. Or if you know about mixed substructure. Okay.
Do we have a weak factorization for that?
Say it again?
Do we have a weak factorization for complete plans?
That's basically what we do. That's basically what we do. Yeah. Okay, so I want to try to explain what these two underlined notions are, and give you one slide of the proof. And let's see. So here's what it means to be a tropical homology manifold, at least intuition wise. I won't get into all the details. I do want to say that this is kind of how our conversations for this joint work started, was that Edward and his in his master's thesis, was looking at this notion of tropical Poincaré duality and when fans have tropical Poincaré duality. So, and then later, Amini and Picaraz also had a paper that they put on the archive. Edward didn't put his on the archive right away, but it was nice to come together, join forces, and show that this concept is actually useful, at least in solving the problem. So there's a notion of Poincaré duality for this homology theory. And if you know about the Doric category and Verdier duality, you should really think that this is computing the Verdier dual of the sheaf Fp and asking that it is Fd minus F to the d minus p, where d is an empty space. If you are more familiar maybe with like Hatcher style algebraic topology, then maybe you remember the the cap product and how the cap product, even for a non-compact space, I've written X here and a U here, okay, but can specialize this to a U, would go from say cohomology, gives a map from cohomology, capping with the fundamental class to the Burrell-Moore homology. And it looks like this.
Is there an implication between the or writing every operationality?
Well, I'll get to, yeah, thank you. Okay, but let me first just say, so what it means that Poincaré duality for X is if I put X here, and X here, that this map is an isomorphism. Then X has Poincaré duality. If I want it to be a tropical homology manifold, then I'm asking for that to hold on every subset, open subset U. Right? I said I can do fancy things when I described tropical homology, and then I can even take open subsets. I want this to work for every open subset.
Do we want to think about all open subsets?
You don't have to, but this is one way to do it. I could also say you could take every open star of every cone, and then that's enough too. Okay? But somehow then I don't have to have sigma, like little sigmas hanging out here and just right. But you're absolutely right that that's kind of too strong. But this kind of helps make an analogy with what it means to be a homology manifold. Okay. Well, we also know that in usual manifold theory or usual cohomology that not everything that has usual Poincaré duality is a homology manifold. And I don't know the answer to that question here. So I don't know of any fan X which has Poincaré duality that has a cone that doesn't. I think for the Chow ring this doesn't work. If the Chow ring has Poincaré duality, then does every open star have Poincaré duality? I don't know. Okay, let's stop. I think maybe I heard that being whispered at some point, but maybe that's a map overflow question. Okay, so we really do need this on either every open set or equivalently every open star. So this one has tropical Poincaré duality. This one doesn't. Yeah.
I'm just like a little bit confused by the like normally you think of a manifold like as like the link of a point is a sphere. But in this like diagram here, like the link of the origin looks like 3 points, not like a sphere.
Yeah, so I mean, yeah, like you're saying that, I mean, this is not a usual homology manifold by any means, but it's a tropical homology manifold. And I guess maybe the thing is coming in with, we're changing not just the index of the dimension, but we're also changing the sheaf. Instead of FP, we're taking F dim X minus P. We can do some examples after I talk. Okay. So it was shown also by myself and some co-authors that no matter what matroid you take, the support of the matroid fan is a tropical homology manifold. So this holds for not just matroid fans, but well, of course, every cone of a matroid fan, the open star is a matroid fan. So you show it for matroid fans, you show it for, they show that it's a tropical homology manifold. One of these papers was over Q and the other paper was over Z. So there is a Z variant. This. Okay. If you like, this is something that's really just on the combinatorial side, okay? No matter how obscure it looks. Yeah?
There's a paper of Gross and Shook here where they prove tropical Poincaré duality for a tropical abelian variety.
I think what they prove is they actually reprove this in the language of Verdier duality. So
So a tropical abelian variety is a tropical homology manifold.
Tropical abelian variety is actually a manifold. It's actually an integral, yeah, okay, manifold. But they prove it also in the sense. We might be talking about two different papers, but certainly they prove something more general that they reprove the statements, and this statement also generalizes not just the matroid fans, but things that are locally matroid fans. And tropical abelian varieties are locally Rn, which is a matroid. Yeah.
What are the conditions on X? Any subset of RGBM or?
So in this definition, I'm only really thinking about X being fan, but you can put any thing you want there that has at least, a tropical structure. You need this fundamental class comes down to the existence of this is that you have a balanced polyhedral. I also didn't describe what this is, but you need balancing. this, you're encouraged to think about this in analogy with usual algebraic topology. Unless you know what some of the ingredients. Okay. So that's that described. Now, here's a definition of wunderschön varieties. So a variety is wunderschön with respect to some sigma. So we actually don't really need with respect to sigma there, but okay. If it is schön, and for every, no, okay, sorry, I see what. And for every cone sigma of the fan big sigma, this variety we need it to be connected. Okay, and for every k, the mixed Hodge structure on HK of the stratum X sigma is pure of weight k. Okay. So if you know, this is extremely strong. So we're also not just asking that X itself has pure mixed Hodge structure, but also all strata. And this ingredient here, that it's connected, is also extremely important. Okay. Like I said, it's an if and only if. So it would be nice to be able to try to relax some things, but from what we're asking for, we're kind of stuck. Okay, so if you know what a mixed Hodge structure on this X is, that's great. I'm going to show you at least a little bit of how you get it in a second. But let's just go through first what are some properties of these things. So if you have a one-dimensional algebraic variety that is wunderschön, then it has to be a rational curve. Okay. Already kind of boring a little bit. Can't have anything of higher genus. And each of these strata have to be a single point, right? Because they're connected. If the strata are going to be zero dimensional, they can't be multiple points. They have to be single points. This connectedness assumption also tells us that the tropicalisation, so Kumar was asking about weights, the tropicalisation has to have weight 1 everywhere. That's what the connectedness assumption tells us. This pure mixed Hodge structure also tells us that the odd cohomology of all of the closed stratas has to be 0. It only has even cohomology when we look at the closures of everybody. Being wunderschön is also already enough to tell us that the tau star is surjective. And that the cohomology of the closure, and actually I can put a sigma here, is algebraic and also divisorial. That means the cohomology ring is generated by the things in codimension in degree 2, multiplicatively. Okay. And the last thing is that on our motivating example of these linear subspaces of the open torus, that these are so-called wunderschön. This is not the language of Shapiro, who proved it. Shapiro proved that pure mixed Hodge structure is pure as the right thing.
So if you choose the right sigma.
Say it again.
If you choose the right sigma,
Yes, thank you.
not any sigma.
Okay, let's say, yeah, thank you.
Shouldn't
Mhm.
the attribution there go back to like Ulrich and Solomon? Because they proved the cohomology is generated by these classes in H1, and you look at them and they're weight 2 classes.
Okay, Shapiro has this paper where he really goes through the mixed Hodge structure of the complement of an arrangement.
Okay.
What's the condition in the first property of V9? What's the condition V9?
Oh, sorry, I was using a different notation for the vertex of the fan. The vertex of the fan I had called 0, so, right, the stratum of any of the rays is going to be a point. Okay.
So this P1 with 4 answers is not position.
It is.
But
It doesn't have-
why this fan?
It doesn't have Poincaré tropical Poincaré duality. Yeah.
That isn't a different.
No, so the theorem says that you have to have both.
I need to have both.
If and only if and. Thank you. Okay, so this example, when I had okay, remember I showed you that this thing was the tropicalisation of 2 different things? If you take the single sphere with 4 punctures, that's wunderschön,
Right, yeah.
right? But I tried to convince you that you weren't recovering the cohomology in that case, and it's because you're not satisfying the tropical Poincaré duality. Yeah, so yes, no. Okay. Okay, so here's a little bit of a snapshot of the proof or how the proof works, and to say a little bit more about what it means to have a pure mixed Hodge structure. So the mixed Hodge structure is coming from the Deligne weight spectral sequence, which if I cover up this thing, these are the kind of even rows in the beginning page of this Deligne weight spectral sequence. So it's a spectral sequence that's, I mean, the first pages are starting with the cohomology of the compactification of the closed things. And what this spectral sequence is going to do is compute for you the cohomology of the open part and give you a filtration on that cohomology. When you are wunderschön, what it means is that this is exact. And the odd rows, without adding anything here, the odd rows are all exact. So all the odd cohomology is there. Okay, so this thing here is exact. And having tropical Poincaré duality is implies that you also have a kind of analog of this Deligne exact sequence for the tropical cohomology. So this is the open thing, and then we have closed stratums here. And this is also exact. Okay, so you basically need to prove that this diagram commutes. When you put taus here, proceed by induction. And when k is big enough, you're done by induction. There's a tricky step when k is equal to 2, where you actually have to do some dirty work. Okay. The other thing that we see from this diagram in the commutative algebra is that just from the commutative algebra, basically we get a map here. And we can, so this is the open cohomology where I started the discussion in my talk, where we didn't have a map tau star here, but now when we are in the satisfy the theorem and everything is isomorphisms, we get an isomorphism. Okay, so we're back to the original question. All right. I think I won't give my very last slide, which was also a motivational slide, but I'll give this one. What we're kind of lacking, I think, is examples of these cohomologically tropical varieties, or even just wunderschön varieties. So, in dimension 1, we've completely classified wunderschön varieties. Convinced me of that. Can also classify what it means for this X to have to be a tropical homology manifold in dimension 1. So-called simply balanced means all the rays should have weight 1, and there's only one linear relation among the directions of the rays, which is, I mean, has to be in the bottom. So we know cohomologically tropical varieties in dimension 1. Higher dimensions, kind of far from any kind of classification, but Edward gave some sufficient conditions for when we take P2 to be, X to be P2 minus an arrangement of not just lines, which we know works, but also conics. There's also this notion of quasi-linear varieties due to Nolan Schwab, and they also are all CT varieties. So here's an example of maybe an interesting quasi-linear variety, the moduli space in general position hyperplanes, P r minus 1. This is quasi-linear when r is equal to 3 and n is less than 8. So if you think you might know some examples of wunderschön varieties, where you have an idea of how to solve the question of is every fan that satisfies tropical Poincaré duality a tropical homology manifold, these kinds of things. That's it. So I'll just show this and paraphrase it. But this is one motivating example for this stronger condition of recovering the cohomology, not just of the open variety, but on all strata. That you could say, well, you ask too much. Like that's why you have such strong conditions on your varieties. But one reason for asking that much is that it allows us to go to tropicalizing not just one variety, but families, and recovering mixed Hodge structures on the families. So this was the motivation of this tropical cohomology of Itenberg, Katzarkov, Mikhalkin, Zharkov. And what we can do with this new definition of cohomologically tropical is basically upgrade their theorem to not asking that the components of a degeneration be linear, but asking that they be cohomologically tropical. And then we can still recover Hodge numbers from mixed Hodge information about mixed Hodge structures and even Hodge numbers from the tropical. Okay, so I'll stop there. Sorry I wanted to end 5 minutes early.
Any question?
General big question. So what are some of the advantages in passing a possible function to possible maybe intersection theoretic? problem to a proper thing.
Becomes combinatorial if you can decipher it, right? So I mean, this idea of recovering cohomology of algebraic varieties from combinatorial models, this works for toric varieties. And not only does it make computations for, you know, intersection theory and toric and cohomology of toric varieties easier, but it also leads to proofs of like a G theorem and looking at numbers of faces of polydopes.
What's the G?
Or just the condition, like the, if you like, it's a complete classification of F vectors of polydopes. Simplicial. But then we're in the smooth.
Can you get anything about the Grassman? I know it doesn't fit in your.
Can you do Schubert? Yeah, so let's talk. Yeah.
What if you augment your tropical data to include, for example, the cohomology of the initial degenerations themselves?
Well, yeah, sure, but then you're just doing an Itenberg spectral sequence. I mean, that's kind of for free. So the kind of answer, the question we're asking is, when is the cohomology combinatorial? And in fact, like with this recipe, you might have another combinatorial recipe that I would love to hear, but I feel like that's even cheating too much to be like, just put the cohomology on every face and then.
But but you still probably need something like the tropical homology manifold condition, right?
Possibly in order to, yeah. That's, yeah. But I mean, if we go back to the original question, which is just, you know, tell me the cohomology of the open bit, then I mean, that's what you just did, right? So you're gonna say, put the cohomology of the variety X on that face.
I guess I'm just wondering if there is an interesting generalization along these lines that contribute. I mean, because you're imposing very strong conditions on these initial degenerations, but basically you could interpret that as saying that they have no interesting cohomology themselves, right?
Exactly.
So maybe
what you'd want to do is, you put what you suggest as the sheaf on your tropical variety, and then like, what's the Verdier dual of that? Does it happen to be the complementary dimensional homology group? Yeah, I don't know. Felipe, you choose.
David, you had your hand out at the beginning.
So as I understand it, if I have any unimodular fan, I now have all of these HPQ groups I can associate to it. And the KK groups are the Chow groups.
Yeah.
What are the other PQ groups?
Exactly, I don't know. But when you have Poincaré duality, tropical Poincaré duality, they're all zero.
Okay.
So you kind of know that I'm gonna get the indexing mixed up, but if you look at the Hodge diagram like this, one side is all zero already for a fan. So having Poincaré duality is this reflection kind of through the origin. And so the one side being zero tells you that the other side has to be zero if you have Poincaré duality. The other ones, I don't know. I would love to know what they mean combinatorially for the fan. And I mean, already, so they are different cellular sheaves that Brion uses, but in that kind of rather, when was that paper from? I can't remember, but definitely predates all of this. But there are also, you know, all these bi-graded invariants of fans that in some cases are related to the cohomology of toric varieties, but in other cases, he doesn't know what they are either.
In the definition of your definition of cohomologically tropical, you have this map tau star, which is an isomorphism. Is this isomorphism with rings or just degree wise?
Yeah, thank you. Good question. Where did it go? It's a ring isomorphism.
Ring isomorphism.
It's a ring isomorphism.
Do you think that?
So this is a ring morphism. Already wherever it went, and we asked for it to be a ring isomorphism. Thanks.
Do you think that there's a shot of sort of relaxing the conditions of the theorem if you just want a degree wise isomorphism?
I think based on how this works, it doesn't make a difference. Yeah. That is my guess, but yeah, that's a good question.
You mentioned that all the realization space of matrix are cohomologically tropical, right? And
no, the L's themselves, or the points in the realization space of the matroid correspond to the variety, and that variety is cohomologically tropical. And then there are some instances where the realization spaces are. This in a sense, another realization
Yeah.
space.
I was wondering, you said something about balancing conditions, also that the underlying fan needs to satisfy balancing conditions or some choice. Right, so my question is, I was wondering, if higher balancing conditions are somehow related to this work on balancing of themes and classes and their higher statistics coming from
I see.
vector
So
conditions.
maybe one question that I would formulate out of this too is Matroid fans have these CSM classes, they have this kind of higher balancing thing. Do these wunderschön varieties, sorry, these cohomologically tropical varieties, their tropicalizations should also have characteristic classes kind of following the same definition. I would imagine they would be balanced, but I'm crossing my fingers because I haven't checked it. But that's something that may be worth checking.
Just in this particular realization space where Schock had claimed that for 3 and 8, it's quasi-linear.
Is it wrong?
It's not. Yeah.
Oh, okay.
Dan Corey found a counterexample, and I think Schock updated his.
Thank you. So should I, do you know if I can update this to a strictly lesson 8 or is it good for 7 or is it not good at all?
I don't know. I just know that 8 is wrong.
Okay, I hope that this part of the video will be up. Okay, so let's write this and then question mark. Thanks. I'll check the updated version. Thank you, Sam.
Yes.
Can you say briefly how the tropicalisation is related to what algebraic geometers call toric degeneration?
How it's related to torture? Well, I mean, I don't know if I can say exactly how it's related, but I can tell you that points in top dimensional faces of the tropicalization are rather good candidates for toric degenerations. So this is not giving you a toric degeneration, but I mean, initial degenerations, right, are indexed by the Grosvenor fan, and this is some subset of the Grosvenor fan, and this is the top dimensional. So Kumar is a person to ask about this as well. That top dimensional faces points, like initial degenerations coming from points in top dimensional faces of tropical varieties are candidates for generation, but not necessarily always such.
Probably are with your hypotheses, or
say that again.
They may well be. You're putting. I mean, they're likely to be with your hypotheses. I guess.
That's a good question. I don't know. Yes, that's. Yeah, I haven't thought about it, but it's worth thinking.
So what's the question?
I think they probably are. The connectedness, multiplicity, one and connected.
That's not enough.
Might be enough.
That's not enough. But let's talk. Yeah.
Maybe just a couple more questions. Yeah.
Is there a theory ready for arbitrary coefficient sheaf, cellular coefficient sheaf?
You can like what part of the theory do you? I mean, there's a whole machine of derived category of cellular sheaves.
Cohomological comparison between a suitably trivialized sheaf on variety versus.
Not yet, but yeah, but let's talk. If you have some in mind, we can see what we can try.
I have a very vague question. So, and I mentioned Ross and Schock. So they also proved the Poincaré formula on a tropical abelian variety for the Jacobian for the classical curve in terms of the power of the tropical theta divisor. So now that you have your result on maybe on your last slide on the generations, do you think it's possible to reprove their result just by taking the kind of algebraic Poincaré formula and degenerating it, or is that?
I think no. With this, I think what they do is there's more involved, as far as I understand. Like this is also not really saying.
So there is value in proving things tropically. You can't just degenerate kind of classical results this way. The results.
Maybe I shouldn't say anything right now because I'm on camera and I haven't thought about it, but we can discuss it. Yeah.
I asked Farbad the same question 2 weeks ago and he said no.
Okay, thank you. Now I'll go with my initial no. Thanks.
All right, maybe let's thank Kris again.